So our speaker today is Luca Penserini. Luca is a PhD from the Environmental and Infrastructure Engineering program, and he's enrolled in the 37th cycle. He is working under the supervision of Professor Manuel Antonelli and Beatrice Cantoni, and his research is devoted to finding new systems to reuse wastewater for agricultural purposes. So without further ado, I just give the floor to Luca. So the floor is yours.
Thank you, Chiara, for the introduction, and thank you all for being here. So many of the introduction has already been done, but just to recap, I'm Luca Penserini. I'm from the I'm from the Environmental and Infrastructure Engineering School from the 37th cycle, and I work in the Safe Water research group under the supervision of Manuel Antonelli. And my PhD focus on the wastewater reuse in agriculture, particularly looking at its modeling its impacts, and looking at the risk assessment procedures related to it. First of all, why do we need wastewater use? As many of you probably know, water scarcity is like among one of the topic of growing concern nowadays, especially due to many stress factors such as the rapid urbanization or the climate change. And in this context, agriculture is the sector which consumes most water. Here you can see a scheme of a typical agriculture irrigation system. So water is derived from the environment and it is used to irrigate crops. And typically in crops are also added mineral fertilizer, which contribute to the generation of greenhouse gas emissions. And these crops are then consumed by people. In addition, the same fresh water that we use to irrigate crops from the natural environment is also the place in which many wastewater treatment plants along the water course discharge their effluents. So in this perspective, it becomes interesting to see the wastewater not as a waste, but as a resource and an alternative source for irrigation water. Why? Because we reduce the use of fresh water, and at the same time the effluent is rich in nutrients, so we can exploit that to replace the mineral fertilizers. It's important to specify that reuse can happen in two ways. We can have direct reuse, so the wastewater is collected to the irrigation system by a dedicated network, or we can have indirect reuse, which is basically what de facto is happening. So water is discharged into the environment and then it's used from the environment to irrigate. But it's important to keep in mind this differentiation. In any case, many impacts are related to this practice. The positive ones, we already seen them, so water and nutrient recovery, but from the negative side, we have potential compartment cross-contamination, we have the increase of salinity due to the salinity contained in the effluent of the wastewater treatment plant for crop and soil. We can have environmental risk or human health risk. So the first need is to develop a comprehensive framework which can evaluate these multiple impacts simultaneously and in the correct way. From the regulation point of view, wastewater use is encouraged by the regulation. In fact, the water quality for direct reuse is already regulated at the European level, which defines 4 quality classes for water. And another important aspect is that into the regulation there's a particular focus on the adoption of risk management plans. This procedure, let's say, is stressed not only in this regulation but in many regulations dealing with water. But if from one side we need to implement risk assessment procedures as preventive measures to manage the water system, On the other side, it's not really clear how to perform risk management approaches or where and when to apply them. Why this? Because we have many procedures for the risk assessment that they can address different endpoints. So, for example, the environment or the human health. And just to specify, when I'm talking about risk, in this case, I'm talking about human health risk, so due to the ingestion or inhalation of contaminants, and a risk for the aquatic ecosystem due to the toxicity of contaminants. So we have different endpoints, we have different targets, so chemicals and microbials. We can have different toxicity effects, so acute and chronic, but all these procedures are already developed, but they are implemented as standalone tools and not implemented together, while these risks happen together. So the second need is to develop this a sort of integrated risk assessment procedure that allow us to evaluate the whole system and not just a particular aspect of the system. In this perspective, my PhD research is aimed at developing a comprehensive risk assessment, risk-based framework to assess all the impacts that are related to the wastewater use practice in order to support a sustainable implementation. This work, this research is articulated in as follows. So, first of all, literature review was performed to evaluate what are the typical models adopted for evaluating the impacts. Then a prioritization framework was developed in order to support the implementation of wastewater reuse projects. And as last, different models for the integrated evaluation of different risks have been developed. In particular, first, it was compared the risk due to multiple exposure pathways, so food and drinking water. Then for multiple endpoints, so environment and human health. And lastly, from multiple targets, so from chemicals and microbials. Of this work, the first three are completed, while the last two, I will perform them during this last year. So, starting from the first one, as I said, the literature review was performed, and the aim was to identify like the gaps, but also the research direction for wastewater use model, impacts modeling. 163 articles were collected and analyzed from the latest 6 years, and they were classified based on this conceptual framework, which basically is based on three key characteristics, which are the compartments. So we identify 6 compartments, which are the matrices where the wastewater use implied. The impact models, we identified 10 types of impact models. Each model is related to one specific type of impacts, and 9 targeted variables. The variables are, we can call them also the contaminants, let's say. So what the models is evaluating. The first outcome that came out from this literature review is that the largest fraction of the study in literature deals with direct reuse. Why? Because from one side, probably indirect reuse is not technically considered as our use, even if it's applied in many cases. And on the other side, the direct reuse is the only one regulated. The second output from this literature review was this heat map, which allowed us to like investigate what are the more consolidated correlation among different categories. Again, there's the differentiation between compartments, model, and variables. And on the other side, which are the gaps? So from this literature review, we obtained 2 main outcomes, which leads us to the next task that I will present you. The first one is that a prioritization methodology for for the implementation is missing in literature, actually. And on the other side, that the integrated procedures evaluating different type of risks are currently missing. So, starting from the first gap, the question is, okay, we have a regulation that tells us we must do reuse, but we don't know how to select where I should do reuse, because typically water utilities, they manage maybe hundreds of wastewater treatment plants, and they can't implement reuse on all of them, because it's a matter of cost in the end, because you should allocate money and so on. So the idea is to develop a prioritization framework, and we focus on not considering just the wastewater treatment plant characteristic, but also the surrounding territory characteristics, to decide where it is better to implement reuse. So this work is articulated in 3 steps. In the first one, a techno-economic model was developed. In the second one, data were collected, and most importantly, the wastewater treatment plants that we had available, they were classified. Why this? Because the classification enabled us to not study all the set of wastewater treatment plants that we have, but identify representative wastewater treatment plants and use them as an example, like the same results that we obtain for them, we can extend to the other wastewater treatment plant. Then the model developed in the first step was applied only to these representative wastewater treatment plants. So starting from the techno-economic model, as I said, for this model we're considering both the wastewater treatment plants characteristics. So the first 4 that you see basically are effluent characteristics. So we have the nutrients, nitrogen and phosphorus, we have the flow rate, and we have the electrical conductivity. Why the electrical conductivity? Because it's a proxy of the salinity content of the wastewater. But also territory parameters were considered. We consider the type of crops surrounding the wastewater treatment plants, their crops, water and nutrient requirements, their sensitivity to salinity, because it differs between different type of crops, and the effective rainfall, so weather characteristics. Then these input were fed to the model, which determine as output 4 outputs. The first 3 are positive outputs, the last one is a negative one. And first, these outputs were quantified in their respective unit measure. So we quantify how much primary fresh water we can save, so in terms of volume for a year, how many kilos of mineral fertilizer we can save with wastewater use. The same with avoided greenhouse gas emissions. And lastly, we quantify what is the crop yield loss due to desalinization due to wastewater irrigation. Then all these 4 outputs were converted into economic terms to have a single output to evaluate them uniformly. Moving to the data collection, 2 areas were considered, so the province of Brescia and the province of Udine. 95 wastewater treatment plants distributed across these 2 areas were considered, and data were collected from them. Then, as I said before, these 95 wastewater treatment plants were classified into, by adopting 3 classification criteria. So, depending on their size, so identify 3 classes of size, on their level of nutrient removal. So we have no nutrient removal, means that the effluent will be rich in nutrients. Just the nitrogen removal, so the effluent will be rich in phosphorus, or nitrogen and phosphorus removal. So the effluent will be poor in nutrients. And finally, the type of crops. We identified 2 types of crops, so seed crops, and specifically we consider maize and soybean, and fruit and vegetable crops, and we considered vines and carrots. In this way, we identified 10 classes of wastewater treatment plants, which are reported there. And the results are obtained for these 10 classes. Here you can see, let's say, an overview of the results. I try to drive you through the graph. So in the top chart, you can see the classes of which I was talking before. Then, looking at the graph, we have the column, which refers to the left bar. And the left bar reports the net annual saving, but in terms of units of area. So for each irrigated hectare of crop, of land, how much is the saving? And it is differentiated between the 4 outputs I was explaining before. While on the right side, and while the dot points refer to the right column, and there is reported the potential annual saving, which is the maximum saving that I can obtain if all the wastewater treatment plant flow rate is used to irrigate the crops. And this graph can use or by looking, like, I want to know in which class my wastewater treatment plant is, or I can say I have many wastewater treatment plants in which it is better to implement reuse. So this is the use of this kind of output. The main outcome that we can point out are that the crops type are the most relevant parameter, and at the same time it is important to consider not just the positive impacts but also the negative impacts, in this case salinization, because it can overturn the result. So for some type of crops it becomes not convenient at all to implement reuse because you have a loss and not a saving. Here I show you, like, the first one was the generic results. Here I show you the results applied to the province of Brescia because we implement the model on that. So here you can see what you were seeing with the dot points, so the potential savings. Each dot is a wastewater treatment plant. The bigger the circle, the bigger is the potential savings. So the idea here are some of the classes analyzed, and each, let's say, here you can see the type of crop and the specific class of the wastewater treatment plants. And the goal is, okay, this is the situation for the ones that we analyzed, but we want to extend the results to all the wastewater treatment plants that are in the province of Brescia. So this is the generic idea and how it can be implemented. And from here, what we can see that these circled wastewater treatment plants are the most convenient in terms of reuse implementation. So the conclusion is that we can say from here that the biggest is the wastewater treatment plant, the highest is the potential saving, especially if it's surrounded by vines, in this case. This work has been written and submitted recently, so finger crossed. While moving to the last part, namely the last gap, so the risk part, I need before this to do a brief overview of the risk assessment procedure. So first of all, what we typically address with risk assessment procedure, we have 2 types of contaminants. On one side, the microbial, which are responsible and the microbials, and among microbials, the pathogens. Pathogens, I think many of you know them, but they potentially they could cause diseases for human health, and they typically have acute toxicity. So the effect, we can see immediately after the consumption of them. We have different types of pathogens. There are some pictures, but they are pretty much well known. While for the chemicals one, there's this big class of contaminants, which are the contaminants of emerging concern, which are persistent chemicals that are potentially hazardous both for humans but also for the environment. And they derive, the concern is due to the fact that they derive from common use. So we can have them from domestic use, from agricultural use, for industrial use. And here you can see some examples. So we can have the personal care products, the pharmaceuticals, the pesticides, the perfluorinated substances. But what is the problem with these substances? Is related to their uncertainty. Why? Because they are present, but yet really toxic, even at low concentrations. So there's a challenge from the analytical method point of view. They are not yet regulated, and their regulation is evolving in time. And finally, there's a lack of toxicological studies about them, so it's difficult to quantify their related risk. Talking about our risk assessment procedures include risk, we have for the microbials, they already exist probabilistic approaches capable of including uncertainties in the risk quantification. In particular, there's this procedure called quantitative microbial risk assessment, which includes the uncertainty. While for the chemicals, only deterministic procedures are available, and they are not really able to properly account for uncertainties. So the next step is to, let's deepen the chemical risk assessment. Typically, the risk assessment is performed articulated in 3 steps. So we have an exposure assessment, and this is valid both for human health risk, but also for the environment. So the exposure assessment is aimed at quantifying the exposure concentration. So it could be the surface water concentration if I'm looking at the environmental risk, or the crop concentration if I'm looking at the risk due to crop consumption. Then there is the hazard assessment, which is the part in which, with toxicological study, we determine what is the maximum tolerable concentration of exposure. And finally, we combine these 2 steps and we obtain the risk characterization, which quantify the risks. Nowadays, how does this procedure work? We find the worst case parameter, so typically the maximum exposure concentration and the minimum threshold values. We combine them and we obtain the risk. The risk, simply, if we are above 1, we have a risk. If we are below, we don't have it. This means a deterministic procedure. What is the next step? Is to move from the single point evaluation to the distribution, to evaluation of the distribution of points. So here we can see the uncertainties related to the exposure. Here you can see the uncertainties related to the toxicological characterization. And a procedure has been tried to be developed in the previous year called quantitative chemical risk assessment, and is reported in those papers. And the result will be that we don't have anymore a single value for a risk, but we have the distribution of risk. So we can also take more conscious decisions. After all this, we move to the 3rd task. So the 3rd task, the goal was to investigate which is the contribution of wastewater use in terms of risk compared to the whole anthropic cycle. So basically we compare the risk due to the consumption of crop with the risk due to the consumption of a common exposure pathway, in this case the drinking water. So we compare quantitatively the risk between food and drinking water. This work has been based on literature data. We studied 144 articles and we classified them into this framework, identified 10 compartments, which are the one in yellowish green, and we targeted bisphenol A and anilphenol A, which are contaminants of emerging concern frequently present in drinking water and food, in particular in the packaging, due to the release of their packaging. Then the QCRA was applied to tap drinking water and food, in particular food, looking at cereals or fruit and vegetables. Here you can see how the bisphenol A and anilphenol are distributed among the different compartments. And in particular, you can see that the last 4 compartments, which are the solid matrices, they contain the highest concentration of these contaminants. compared to water matrices, which are the one on the left. Then we just focus on these three compartments, and there you can see an example of output. So the red line up there is the presence of risk. So risk EQ is a benchmark quotient, which is an indicator for risk. So above that level, we have a risk. And we can see that actually for food, there's an important contribution to risk. So what emerged from here is that also crops are an important exposure pathway for contaminants of emerging concern. So they should be monitored in the reclaimed wastewater. This work has been published recently. And so talking about contaminants of emerging concern, this is again the scheme that I presented at the beginning. We see that the orange dots are the contaminants of emerging concern, and they can spread all around the system. But talking about reuse, as I mentioned before, we have two types of reuse. So we have the direct reuse, so we don't have the surface water, but the direct reuse, it can only bring to risk for the human health. On the other side, we have the indirect reuse. That can both bring to risk for environment and human health. So this is the scheme, and as we've seen before, only 15% of the studies address indirect reuse. In addition, there's not a different type of risk, but also each contaminant can have different type of risk. Here, this is a graph from the same literature review of the first task, and here I reported 6 contaminants, which are just representative. It's not important which contaminants are. But we can see that here is the risk on a logarithmic scale. And the red one is the human risk of these contaminants. The blue one is the environmental risk of these contaminants. And we can see that for every contaminant, there's a sort of different behavior. So we have the first 5 contaminants have the environmental risk higher. The last one has the contrary. For the diclofenac and ibuprofen, we have an environmental risk which is above the threshold level. So in this perspective, it is important to identify a procedure to prioritize and, let's say, classify the contaminants, because we have a large amount of them present in the environment, but we can't address all of them in the same way, or, for example, monitor all of them. And we need to prioritize them, and the idea is to do it based on both the environmental and the human health risk, which usually are evaluated separately. How to do that? We evaluate the concentration in both crops and surface water to have both the exposure concentrations, and we try to prioritize these contaminants of emerging concern based on 2 different risk methodologies. The first one is the QCRA, which we saw before, and the peculiarity is that is based on concentration data, on measured concentration data. While the second one is this procedure called typool, which is based on molecular descriptors, which are a characteristic which is intrinsic into the molecules. So we don't need as many data as the other procedures, but probably we will have an evaluation, let's say, broader, but less detailed. So this is the comparison that we want to make in this case. Finally, moving to the last task, here the idea is to, as I said before, we can have chronic or acute toxicities, and the idea is to integrate them. But the challenge, is that the acute toxicity happen in really short period, while the chronic toxicity is a toxicity that you can have over a lifetime period. So here the challenge is to here the challenge is to find a proper time horizon which enable us to consider both this type of toxicities, which they happen at the same time, but they are not, but they are quantified separately. As an example, if I have a water treatment, typically the more I reduce the level of microbial contamination, the more I will have to dose chemical compounds. So on one side, I'm lowering the microbial risk, but on the other, I'm raising the chemical one. So the idea is to combine them, and by combining the two procedures which I mentioned before. And finally, for these last tasks, I'm performing a monitoring campaign from which the data will be used to validate the task 4 and 5. So data were collected from this monitoring campaign. In particular, a wastewater treatment plant in Rovato will be analyzed during two different periods. 4 sampling points will be analyzed, so the river before and after the discharge of the wastewater treatment plants, and the effluent before and after the disinfection, and different contaminants will be analyzed. In particular, we are looking to 14 contaminants of emerging concern, plus 34 PFAS, which is a class of contaminants of emerging concern, but a bit different. 3 pathogens, different E. coli pathogenic strains, and antibiotic-resistant genes. And so to wrap up and conclude, from the first task, we identified the gaps related to wastewater use modeling. A prioritization framework for the implementation was developed, and it has been shown as how quantitative risk assessment procedures can be used as a preventive approach to support the management of water systems. As future developments, what I showed in the task 4 and 5, so a methodology for prioritize contaminants of emerging concern based on the overall environmental and human health risk, and the development of a procedure to integrate the chronic and acute toxicities due to microbial and chemical contamination. That's all. Thank you for the attention.